Welcome back to Math 104. We begin video set number 7. Now that we've looked at the binomial probability model and seen a number of examples of its use, we can ask, how can we use it to solve problems involving expected value? Here's one of the examples we looked at of the binomial probability model in action. In a certain die rolling game, each time you play, you roll a pair of fair dice, and if the sum equals 8, you win that particular roll, and you can win more than once if you play several times. Because these are fair dice, we were able to reason out that on a single roll of the dice, there is a 5/36 probability of having the sum equal 8. To recall why that's true, there are 36 equally likely outcomes, and out of those 36 equally likely outcomes, there are precisely 5 of them that I'm circling here that are in this event that the sum equals 8. On a single roll, there is a 5/36 probability that the sum equals 8. Now it's true that there are many different outcomes. There are 36 different outcomes in this experiment. But it's also true that each time you roll a fair pair of dice, either the sum equals 8 or the sum does not equal 8. And therefore, you can think of each roll of the dice as a single Bernoulli trial with probability of quote-unquote success, little p, equals 5/36. So this is regarding the sum equaling 8 as a success. The conclusion is that finding the probability of k, however many k is, k wins in 3 plays of this game, for any value of k between 0 and 3, is a job for the binomial probability model. Because this event is the event that there are a certain number of successes in a certain number of trials, where each trial has only 2 possibilities. The sum equals 8 or the sum does not equal 8. Now here's our question. If you play 3 times, what is your expected number of wins in the mathematical sense of the word expected? In other words, if the experiment is to play the game 3 times, and take note of the number of wins in 3 plays, specifically, we're counting the number of wins in 3 plays, the number of successes in 3 trials. And if you keep repeating the experiment, then in the long run, what will be the average number of wins per 3 plays? That's another way of asking the same question as our original one about expected number of wins. Expected number of wins in this mathematical sense means the same thing as long-term average number of wins. Or, in other words, here's another formulation. Suppose you hold a very large tournament devoted to this game in which every participant plays the game 3 times, and therefore, each person has a certain number of wins in those 3 plays of the game. If you ask each person on their way out of the tournament, how many times did you win in your 3 plays of the game? And then you average their answers to this question, we can ask, what would that average be? If a large number of people play in this tournament, then we see something pretty close to the long run. And so this question, what's the average number of wins among participants in this tournament, is approximately the same question as the first 2 formulations. To compute the expected number of wins, we need to know all the different possibilities for what the number of wins could be, and for each possible number of wins, what is the probability that you get that number of wins in 3 rolls of the dice. The full list of possibilities for what the number of wins could be is 0, 1, 2, or 3, because the experiment is to roll 3 times, and each roll either produces a win or it doesn't produce a win. For each possible number of wins, we have to ask, what is the probability that you get that number of wins? That's a job for the binomial probability model. So the number of wins could be 0, with probability 3 choose 0, 5/36 to the 0, times 31/36 to the 3. Right? This is the probability of 0 successes in 3 trials. So little p, the probability of success on a single trial, raised to the number of trials, which here is 0. Then probability of failure raised to the number of failures, which here is 3. Or there could be 1 win, with probability 3 choose 1, times 5/36 to the 1, times 31/36 squared. 1 win, 2 losses. Or 2 wins, with probability 3 choose 2, times 5/36 to the 2, times 31/36 to the 1. So 2 wins, 1 loss. Or, finally, 3 wins, with probability 3 choose 3, times 5/36 to the 3. All 3 rolls are winning rolls, and 0 rolls are losing rolls, so times 31/36 to the 0. This expression right here is really just 5 over 36 to the third, because 3 choose 3 equals 1, and 31 over 36 to the 0 equals 1. So we could just write 5 over 36 to the 3, but it is a really good idea to write all of this out to be in the same format as the other expressions. Before going on to the next video, use this information that we've just written down to find the expected number of wins by using our second method of computing expected value.